we shall learn about firstly what are nuclear properties, interaction between spin and a magnetic field, Larmor precession and splitting of energy levels in a magnetic field. Electrons, possess both orbital and spin angular momentum and are thus associated with paramagnetism. Nuclei are pictured as point masses and hence do not possess any orbital angular momentum. Many nuclei, however, have non-zero spins and thus possess spin angular momentum similar to that of electrons. Now, what is nuclear spin? The simplest nucleus is that of a hydrogen atom, and you know that it consists of only one particle, a proton. A proton is characterized by the following fundamental properties: it has mass, it has charge and spin or intrinsic angular momentum. The proton mass 1.67 into 10 raised power of minus 27 kg and charge 1.60 into 10 raised power of minus 39 coulomb are taken as units of atomic mass and charge respectively. The charge is equal but opposite in sign to the electronic charge, because electrons are negatively charged, proton is positively charged. Like the electron, a proton has a spin of half. The proton is a constituent of all nuclei. Another constituent of nuclei is the neutron, which is characterized by unit mass that is equal to that of a proton, no charge and a spin of half again. Thus, a nucleus consisting of p protons and n neutrons will have a total mass of p plus n, ignoring the small mass defects due to nuclear binding energy, a charge of p and total spin, which is a vector combination of p plus n spins, all equal to half. Each nuclei has a different combination of p and n and hence a different spin value. It is very difficult to predict the total spin from the number of protons and neutrons in a nucleus. However, the observed spins have been rationalized and a few empirical rules have been formulated. Thus, the hydrogen nucleus 1H has a spin of half since there is only one proton. Its isotope deuterium 2H has a neutron also, and the total spin could be 0 or 1 depending on whether the two spins are parallel or antiparallel. The observed spin is 1. Helium 2He has 2 protons and 2 neutrons and a net spin of 0. From such and other observations, it can be concluded that nuclei with both p and n even, that is even charge Z. Z is the atomic number which is equal to the number of protons or p, and even mass, that is A is the atomic mass number and this is equal to the sum of p plus n, have 0 spin. Examples are 4 helium, 12 carbon, 16 O, etc. Nuclei with both p and n odd, that is odd charge Z, which is equal to p, and even mass A, that is p plus n, have integral spin. Examples are deuterium 2H, 15N, spin is equal to 1, 10 boron, spin is equal to 3. Nuclei with odd mass A have half integral spins. Examples are 1H and 15N, spin is equal to half, and 17O, spin is equal to 5 by 2, and there are other such examples. The spin of a nucleus is defined by the symbol I, called the nuclear spin quantum number. Just like you had the S quantum number for electrons, you have the nuclear spin quantum number I. Unlike the electron, for which the analogous quantity S can take on only one value half, nuclear spin can take on integral and half integral values and even 0. Spin half nuclei have a spherical nuclear charge distribution, and the NMR behavior, the nuclear magnetic resonance behavior, is the easiest to understand. Other spin nuclei have non-spherical charge distributions and may be analyzed as prolate or oblate spinning bodies. Just like you learnt about rotating molecules, here also you can talk about oblate or prolate spinning bodies. All nuclei with non-zero spins have magnetic moments which are characterized as mu I, and but the non-spherical nuclei also have an electric quadruple moment which is given as EQ. Now, what happens when this spin interacts with a magnetic field? In general, a charged particle spinning about an axis constitutes a circular electric current, which in turn produces a magnetic dipole. In other words, the spinning particle behaves as a tiny bar magnet placed along the spin axis, as we have shown in figure. The size of the dipole, that is strength of the magnet, is proportional to the spin angular momentum, or we can say the vector quantity mu, the magnetic moment, is equal to gamma into the magnitude of the I spin quantum number, and gamma is a fundamental constant called the magnetogyric ratio and has characteristic values for each nucleus. So, this is how we have shown it behaves like a bar magnet. Now, what is Larmor precession? Let us consider the classical motion of a magnetic moment mu I in a uniform externally applied strong magnetic field B naught under the condition of constant total energy. The movement of mu traces out a cone about B naught, as we have shown in this figure. This is precession of a magnetic moment mu about an applied magnetic field B naught. Such motion is referred to in general as Larmor precession. The precession angular frequency omega 0 is proportional to the magnetic field strength that is given by omega 0 is equal to the same gamma into B naught, which is a vector quantity, and omega naught is expressed in radians per second. It is the angular frequency. Now, this was all classical treatment. Let us do a quantum mechanical treatment. According to the classical picture described above, the atomic nucleus, assumed to be spherical, rotates about an axis and thus possesses a nuclear or intrinsic angular momentum I. Quantum mechanical considerations show that, like many other atomic properties, the angular momentum is quantized. That is, just like for the other angular momenta, I square operator, when it operates on the nuclear spin wave function, it gives you I into I plus 1 into h cross psi, where psi is the nuclear spin wave function, and h cross as usual is equal to h by 2 pi, and this is the unit of angular momentum. Thus, the magnitude of the angular momentum is given by the magnitude of I is equal to square root of I into I plus 1 into h cross, where I takes for each nucleus one of the values. It could be 0, half, 1, 3 by 2 up to 7. Only nuclei with spin I not equal to 0 can produce a NMR spectrum. Like other angular momenta, not only is the magnitude of the angular momentum quantized, but also its component along a reference direction, which is usually the z direction. This is also quantized. That means that Iz operator, when it operates on the nuclear spin wave function, it gives you a quantity Mi h cross into psi. The component Mi along a particular direction can take on values. Mi can be I minus 1 going through 0 up to minus I minus 1 and then minus I. That means there are 2 I plus 1 values when I is integral, and when it is half integral, then in the center you have values half minus half when I is half integral. Thus, there are 2 I plus 1 values in each case. Thus, the vector I cannot point in any arbitrary direction, but can point only so that its component along a particular reference direction, that is z, are either all integral if I is integral or half integral if I is half integral. Thus, for a spin half system, you have two values, plus half and minus half, and you will see that these are the only allowed values. The length of the arrow is proportional to half into half plus 1 into the square root of this into h cross, and the components are either minus half h cross or they are plus half h cross. Also, since only I and one of its components Iz are quantized, it follows that since I square is equal to Ix square plus Iy square plus Iz square, that means that Ix square plus Iy square is equal to I square minus Iz square, or if you put in the values, the quantized values, this is I into I plus 1 minus Mi square into h cross square. Thus, though Ix square and Iy square are not individually quantized, the sum of their squares is quantized, can only take on these specific values. The locus of all these points is a cone, and Larmor precession is thus explained. In the absence of an external field, all Mi values will have the same energy. The degeneracy is removed and 2I plus 1 different energy levels will result if an external magnetic field is applied to define the reference direction. You have already learnt about the Zeeman effect. This is what happens. We shall now discuss the effect of such a field. The magnetic moment is proportional to the magnitude of the angular momentum. For a point charge of charge E and mass m, it can be shown that mu I is equal to E by 2m into I, the absolute magnitude of I. The magnetic moment has the SI units A m square, that is ampere square meter, but it is more appropriate to express in terms of the magnetic flux density, loosely called magnetic field strength, whose SI units are the Tesla, for which the symbol is T and its unit is kg second square A inverse, where 1 Tesla is also equal to 10,000 Gauss in the CGS units. The conversion is ampere meter square is equal to kg second inverse square, Tesla inverse meter square is equal to joules per Tesla. Hence, for a proton we may write the magnitude of mu I is equal to E by 2 mp, where mp is the mass of the proton, Gn into square root of I into I plus 1 h cross in joules per Tesla. And Gi is the nuclear spin, G factor, just like you had the electron G factor, here also there is a G factor. This equation can be rewritten as mu I is equal to, the magnitude of mu I is equal to Gn beta n into square root of I into I plus 1, where beta n is equal to Eh cross by 2 mp, and this is a nuclear magneton similar to the Bohr magneton for electrons. Its value is 5.0507835 into 10 raised to the power of minus 27 joule per Tesla. Now, we have listed the characteristic properties of some nuclei. You will see that the proton has the maximum natural abundance 99.9844, and its isotope deuterium is only present to the extent of 0.0156. The spins are different. The nuclear spin of the proton is half and that of deuterium is 1. The magnetic moment is different and the magneto-gyric ratio is different. Frequency in a field of 9.39 Tesla is also different, and you also have many other magnetic nuclei like 11 boron, you have carbon 13, you have 17 oxygen, 19 fluorine, and you also have silicon and phosphorus, and all of these will show NMR spectra, but at different frequencies. Application of a magnetic field causes an interaction between the magnetic moment and the field, and this is given by the scalar product minus mu I into dot product B naught, and this is equal to minus mu z, because the component along the B direction is mu z minus mu z into B0. That is, the magnitude of the interaction energy is given by the product of the magnitude of the applied field multiplied by the component of the magnetic moment in the field direction. The component of the magnetic moment in the z or the field direction, mu I z is given by mu z is equal to Gn beta n mi. Here, instead of I, we are using mi. The interaction energy is thus given by energy of interaction is equal to E int is equal to minus Gn beta n mi into B naught. For proton and 13 carbon nuclei which have I is equal to half, there are two mi values, plus half and minus half, as shown in figure. Thus, if these nuclei are placed in an external magnetic field, they can only be regarded as being effectively lined up with the field mi is equal to plus half, or against the field mi is equal to minus half. As with compass needles in the Earth's magnetic field, the more favorable energy state is the one corresponding to alignment with the field. Since the interaction energy is negative for this state, the energy difference between the states delta E is found to be proportional to the strength of the applied field B naught at the nucleus. Actually, delta E is equal to Gn beta n B naught. As you can see, since mi is equal to plus half or minus half, the difference is equal to 1. So, it is simply equal to Gn beta n B naught, and this is shown in figure. When the field is off, you have both the states having the same energy, but then when the field is switched on, Mi is equal to half will have the lower energy because the energy is given by minus of Gn beta n Mi B naught. So, it is at lower energy, and the beta spin, the Mi is equal to half value is called alpha spin, minus half is called beta spin, and the separation in energy is given by Gn beta n into B naught. And this is shown in figure. Nucleus spin, energy levels of a spin half nucleus in a magnetic field. Now, according to the Bohr condition, transition occurs when a photon of frequency corresponding to the difference in the two energy levels is absorbed. This radio frequency is applied perpendicular to the primary magnetic field, that is along the x or y axis, because that is along the z axis, and this is called the B1 field. This radio frequency is for an extremely short duration or a short pulse, and is thus called a radio frequency pulse. It is much weaker than the primary field, that is B1 is much smaller than B naught. While we have seen that B naught is of the order of hundreds of megahertz, B1 has a frequency of 1 to 20 kilohertz. This frequency is given by nu naught is equal to Gn beta n B naught divided by h. The angular frequency omega naught is equal to 2 pi nu naught, and is thus given by omega naught is equal to Gn beta n B0 divided by h cross. Comparison of equations indicates that the magnetogyric ratio is gamma is equal to Egn by 2 mp is equal to Gn beta n by h cross. Thus, absorption of radiation takes place when the angular frequency of the radiation matches the Larmor frequency, that is resonance occurs. In principle, to observe a nuclear magnetic absorption, we must either adjust the frequency nu naught of the radiation or the strength of the magnetic field at the nucleus B naught, that is until the point where resonance energy absorption occurs, or alternatively vary the magnetic field at constant frequency. Though in its initial decades NMR spectroscopy involved fixed frequency and sweeping the magnetic field until resonance condition was satisfied, that is continuous wave spectroscopy, today's Fourier transform FT-NMR spectrometers use the opposite condition, that is the magnetic field is kept fixed and the frequency is varied until resonance is obtained. Rather, all frequencies are excited at once in Fourier transform spectroscopy. So, we will take up an example, calculate the NMR absorption frequency for a proton in a magnetic field of strength 9.39 Tesla. We have seen that nu naught is equal to Gn beta n B naught divided by h is equal to, can also be written as gamma B naught by 2 pi, and when you substitute the various values, nu naught turns out to be 26.753 into 10 raised to the power of 7 radian per Tesla per second into 9.39 Tesla into 2 pi, that is 2 into divided by 2 into 3.1416 radian, and this is equal to 400 megahertz. This is in the radio frequency range. So, finally a summary. Nuclear magnetic resonance or NMR is a technique which utilizes the nuclear properties to obtain an NMR spectrum. Nuclei with non-zero spin angular momentum possess nuclear magnetic moment. When a magnetic field is applied, the nuclear magnetic moment precesses about it with an angular frequency which is proportional to the strength of the magnetic field. The proportionality constant is called the magnetogyric ratio and is the ratio of the magnetic moment to the spin angular momentum. As with other angular momenta, the magnitude as well as one of the components is quantized. For a given nuclear spin angular momentum, quantum number I, there are 2I plus 1 components of the same energy. But when an external magnetic field is applied, as a result of the Zeeman effect, the degeneracy is lifted. Now, if an electromagnetic radiation of the appropriate frequency in the radio frequency region is applied, the radiation may be absorbed, causing flipping of the nucleus spin, resulting in an NMR spectrum.